Hello guys, good evening.
Good evening, sir.
Okay, we'll wait for others to join, few more minutes and then we'll start. Okay. Am I audible? Can you hear me? Yes. So today we are going to start. Actually, last class what we did, we finished the reaction of epoxide, correct? Like ether reactions we have done the last class, right? Yes, few reactions of ether we have done. Correct. Okay. So we are going to start today a chapter called carbonyl compound. Okay, it contains aldehyde, ketone, carboxylic acid, and its derivative. All those things, correct? So these compounds, carbonyl compounds, shows a reaction which we call it as SnAE reaction, nucleophilic substitution, addition, elimination reaction. Okay. So we'll discuss this reaction first, and then we'll move on to the other preparation methods of aldehyde, ketone, and all, right? That is SnAE reaction, nucleophilic substitution, addition, elimination reaction. So what is SnAE reaction first of all? Write down the heading. We have SN.
Sir?
Yes.
Sir, carbines is over, sir.
Acha, we haven't carbon. Acha, what we
So I
didn't.
thought you said we have, I think, 2 more reactions left.
Yes, sir. You
Oh,
finished
acha.
the carbon compound.
Oh, I forgot. Completely forgot. I'm sorry. Okay, so we'll finish carbene first and then we'll start this. I'm sorry, forgot. Acha, what we did last reaction? Could you tell me?
So reaction of carbonyl compounds.
Acha, reaction. Acha, okay. Few more reactions left. Okay, we'll do this. So we have discussed that KCP, TCP, no?
Yes, sir.
Okay, fine. I got it. Okay, so seventh reaction we have, that is Simon-Smith reaction. We haven't done it. Okay, so we are continuing with the last topic, that is carbene and its reaction. Okay, write down the seventh reaction, that is Simon-Smith reaction. This reaction is similar to the reaction that we did, and that is the first reaction, that is addition on alkenes. Okay, we know singlet carbene gives stereo specific reaction, that is cis molecule gives cis product and trans gives trans. Okay, So here also we have similar kind of reaction, but the reagent we use here is different. Okay, what is the reaction you see? The reaction is, suppose we have an alkene, that is carbon double bond carbon, and if it is allowed to react with diiodomethane, which is CH2I2, in presence of zinc. CH2I2 in presence of zinc. So the product that we get here is C single bond C, and the CH2 group, it get attached over here, H and H, right? Reagent is zinc and diiodomethane. Okay, this reaction is also stereospecific. Stereospecific means the same thing. Cis gives cis, trans gives trans. Okay, how this reaction proceeds, you see, the first step here, zinc is a metal, it releases 2 electron like this. In presence of free electron, the carbon halogen bond, we know it becomes weak. So we have CiH2 plus 2 electron, and it converts into H2C and I like this, plus I minus goes out. I minus goes out. Now this interacts with the alkene mechanism a little bit different, but you can understand it similarly like we did in alkene. So we have carbon, one lone pair, just a second. Then, okay, 2 hydrogen here and 1 iodine present. Okay, so in this what happens, this lone pair, it attacks onto this carbon atom, this pi electron shift over here, and when this attacks onto this carbon, this iodine goes out as a leaving group. Okay, so the product that we get here is C single bond C attached with the carbon plus I minus goes out. This I minus and I minus combines with Zn plus 2 and forms here and forms Zn I2 in the product. Right? Cis gives cis, trans gives trans. Simple reaction. Done?
Yes, sir.
Just a minute, sir. 1 minute, sir. Thank you, sir.
Okay. So, what is the product we get in this reaction? CH2I2 with zinc. Okay, the first one, this reaction is Simon-Smith reaction. The product would be, it is trans, so we'll get a trans product here. This one with CH2N2, what we get here? This gives you singlet or triplet carbene. This one we'll get here triplet carbene, right? And the product would be cyclopropane. Product is cyclopropane here. What is the product we get here in this reaction? Here, the product is a 5-membered ring with nitrogen present in the ring. This is the product we get. Since we are not heating it, see actually what happens if you look at the mechanism of this diazomethane. Diazomethane is CH2 double bond N, where the nitrogen has lone pair negative charge and this nitrogen has positive charge. When you draw the resonating structure here, this lone pair comes over here and this pi electron shift like this and it forms CH2 negative and triple bond N positive. Okay, and then if you heat this, which we are doing over here we are not heating, then this bond pair breaks and it converts into the carbene, which is triplet carbene, plus N2 molecules goes out. This is what the mechanism is. Since we are not heating it here, then this N2 won't release in this reaction, right? What happens here in this reaction? We have ethene, CH2 double bond CH2, and the diazomethane, which is CH2 negative and triple bond N positive charge. This lone pair, it attacks onto the carbon atom and this pi electron shift over here. So this converts into H2C negative CH2 and triple bond N and positive charge on it. Okay, after this lone pair, it attacks into this carbon atom and this pi electron shift over here makes this nitrogen neutral. and hence it converts into a 5-membered ring, which is this. So here nitrogen is not getting evolved since we are not heating it. Clear? Okay. The last reaction in this we have, the 8th one, is insertion on alkanes. We can also write it as addition on alkanes. What happens in this reaction, you see, suppose we have an alkane CH3CH3, and if it is allowed to react with diazomethane and we heat it, so it converts into CH3, CH2 will be there, and one of the carbon hydrogen bond breaks, and this methylene group, it get inserted between the carbon and hydrogen like this. Insertion reaction. If you have methane, then the product in this reaction is CH3, CH2, H. If you have propane, these are insertion reactions, okay? All possible product we get. We get CH3, CH2H, plus we also get CH3, CH2, CH2, CH3, CH2, CH2H. Insertion of methylene group takes place between carbon and hydrogen in this reaction. Done?
So one second.
No, we'll get all possible products here. Not major, minor. We'll get all possible products. The other 8 reactions we have done in this particular topic, that is carbenes and its reaction. Few more reactions we have to discuss. It is not related to carbene, but yes, we'll do in this chapter. And similar reactions we have already done. Okay, and we are going to study these reactions under aromatic chemistry. Aromatic chemistry, actually, it involves the reaction of aromatic compounds. Aromatic compounds, as in, we have benzene, right? Phenols, we can have anilines, etc. All these compounds we consider. Benzaldehyde, benzoic acid, all these things we consider. Right. Phenol's reaction we have done, and the reaction name we call it as electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction, right? EAS. See what happens. What is the difference between benzene ring and a substituted benzene? The difference of this group, and we know this group could be activating or deactivating, activating or deactivating, that we have discussed already. And according to that, we can say whether it is ortho-para-directing or meta-directing. And accordingly, we'll get the product, right? But when it comes to benzene, there is no group attached on the benzene ring. And hence, all the positions on benzene ring are equivalent positions. Wherever the electrophile attach, all positions, carbon atoms are equivalent position. Okay, that's why here we do not have any specific product. Only electrophile get attached to the ring. But if you have a group attached like this, so depending upon the nature of the group, whether it is ortho-para-directing or meta-directing, the groups, the electrophile gets attached to the ring. That is what the difference between the two. Okay, like for example, if this benzene goes under electrophilic aromatic substitution reaction, then it converts into what? The product we get here, if I write down the product directly, the product is this. This E will get attached at any carbon atom because all are equivalent position. How the reaction proceeds? First of all, this pi electron comes over here and this takes this electrophile, right? Electrophile. So what happens here? We get this H will be here, and here we have the positive charge. I've already discussed this, right? In case of phenols. And then this ring tries to gain aromaticity. How do we do that? This H plus comes out, leaving this electron pair behind, and we get the product, which is this. Same thing happens with phenol also. But since OH group is ortho-para-directing, then we get ortho-para substituted product. Okay. If any nucleophile is present here, right? If suppose you have a nucleophile here, then also this ring has no tendency to go under nucleophilic addition reaction and forms this product, NU here. So this product, it won't form. This reaction is not possible, not form. Why? Because if this molecule forms, then the aromaticity has been lost completely, permanently, right? This molecule, again, it is not going to gain the aromatic behavior again. So that's why this ion, which we call it as intermediate ion, or any areninium ion, we can say intermediate ion, areninium ion, or we also call it as a complex here, right? This intermediate ion, it has tendency to gain aromaticity by losing this hydrogen. So it will always go under this reaction, and H plus comes out from this. It won't go under a nucleophilic addition reaction, okay? Because here the aromaticity has been lost permanently, correct? Attack of electrophile, this one is the RDS of the reaction. Okay, now the same thing we have discussed in phenol. A few reactions we have phenol that we have already discussed. Same reaction we have here also. Like if you talk about nitration, here also we have the same reagent and same product we get. Okay, I'll show you some reactions here. Write down examples of EAS. Okay, the first reaction you see, it is nitration. What happens? We have ring, benzene ring, goes under nitration reaction. We can take HNO3, H2SO4, concentrated both, and it converts into nitrobenzene, which is this NO2, and this we call it as nitrobenzene. Okay, electrophile, we know the electrophile for this reaction is what? The electrophile is NO2 plus. NO2 plus is the electrophile. Okay. How reaction proceeds, you see, just I'll write down the steps here. N double bond O and a coordinate bond. HNO3 is this. It reacts with H2SO4, converts into and then from this H2O comes out, plus NO2 plus. This is the nitronium ion, and this is the electrophile for this reaction. Remember the same thing we use for nitration of phenol also. The only difference is we had OH here, which is ortho para directing. So we'll get ortho as well as para substituted product. But when this OH is not present here, all positions are equivalent. So we'll get the same, wherever NO2 attached, it's the same thing. Even it is true for NH2 also, aniline, which is also ortho para directing group. If aniline also present here, NH2, we again get the same result here, right? This is what the difference we have in the two reaction, substituted benzene and non-substituted benzene. Okay, this is the reaction. What all other reagents we can use? We can use other reagents for this purpose, and the other reagents are the first one. We can use HNO3, H2SO4. I won't write this again. We can use only concentrated HNO3. Excess of it we can use. We can also use N2O5. N2O5 is this. Forms NO2 plus and NO3 minus. This is the electrophile again. Okay, these are the reagents we can use for this reaction. Done. Okay. Another reaction is we can do halogenation, we can do sulfonation, all those things we can do. Second reaction you write down, halogenation. And when we do halogenation, we mainly talk about chlorination or bromination, because these two are easier one. Chlorination and bromination. Okay, so what happens in this reaction? Benzene ring with Cl2, and the reagent we use here, AlCl3. Product we get here is chlorobenzene plus HCl. If you use here Br2 with FeBr3, AlBr3, we again get bromobenzene plus HBr. This is what we get. Okay, easily you can understand the mechanism. AlCl3 is a Lewis acid, takes Cl minus, forms Cl plus, which acts as an electrophile, attacks on the ring and gives this product. Okay, the other reagents we can use for this purpose are the first one we can use Cl2 with FeCl3. And all these we can use for bromine also. Only the thing is, for bromination we use FeBr3 here. Cl2 with ZnCl2. Also use Cl2 with BF3. You can also use Fe plus Cl2. Because when these two react, it again forms FeCl3. Right, and FeCl3 again with chlorination behaves in the similar way. Okay, if you want to balance this reaction, we have 2, 3, and 2, and this is the reaction. All these reagents we can use. One note you write down here. Write down one note. In halogenation, all reactions are irreversible in halogenation. All reactions are irreversible except iodination. In halogenation, all reactions are irreversible except iodination. Correct? That is what you must keep in mind. And for iodination, we also use some oxidizing agent, that is HNO3 or HiO4. Okay. Now you see this question. Two reactions we have here. What is the product we get in this two? First one, we have benzene, and this is allowed to react with Cl2 with Fe. ion. And another one, this is allowed to react with Cl2 with Hnu. What is the product we get in the two reaction?
Sir, if there's some phenol group, something attached to
Sorry?
benzene. Sir, if there's some OH group attached to benzene, that's like if it is phenol, then the FeCl3 might react with that, no, sir. So is it possible to do chlorination with phenols also?
Chlorination with phenol.
Yes, sir.
Halogenation, it's possible, no. See, we have done this reaction, phenol, the halogenation of phenol.
Sir, but then FeCl3 or something might react with the OH group, no, sir.
With OH. Phenol
Yes, sir.
might undergo acid-base reaction because the
Yes,
hydrogen
sir.
is acidic over there. But FeCl3 won't react with OH because it is not a basic group. It can accept, electrons. It can take Cl minus from this, can break the C. Actually, what happens? I have written here Cl2 with Fe. Excess of chlorine we are using here. This forms FeCl3, and then this FeCl3 reacts with Cl2. See, there are two things. One is phenol OH here, and chlorine with FeCl3. Because when you have excess of chlorine, it combines with Fe and forms FeCl3, and chlorine is already present because we have chlorine in excess. Correct? So we have FeCl3 with Cl2, and the reaction that you're talking about is FeCl3 with OH here, right? So this
Yes.
OH, it might undergo acid-base reaction. When you have some alkali solution, or suppose if you take OH minus ion here, then this OH minus may easily take this H plus, right? But if you have FeCl3, so FeCl3 can easily break this chlorine-chlorine bond and forms FeCl4 minus and generates an electrophile that is Cl plus. So that electrophile then interact with the benzene ring or phenol, whatever you are taking. Correct?
Yes. Yes, sir.
FeCl3 won't react with OH here. Alkali solution, if you have, then acid-base reaction you can consider.
Sir, I think I'd seen somewhere that FeCl3 is used as a test for phenols. That's right.
As
a test for phenols.
Test for phenol. That reaction,
Yes.
is different. Test for phenols, we have 2-3 tests. That is different. We'll see that. Test,
Okay.
we'll see that in the last when we finish all this.
Okay, sir.
Tell me, what is the product we get in the two reaction? The first one, I have already discussed, it goes under what reaction? It goes under electrophilic aromatic substitution reaction, and anywhere you attach chlorine, it's the same thing. So this reaction is EAS, electrophilic aromatic substitution reaction. But when you have HNu, then it is free radical mechanism. And all this hydrogen here, excess of chlorine we are taking, all these hydrogen is replaced by the chlorine atom, and we get this molecule, Cl, Cl, and Cl here. This molecule, we call it as gamexene, or we also call it as linden. Both are the same name. Benzene hexachloride, another name we have. Benzene hexachloride. Okay, this is the difference in the two. Now, this reaction you see, we have benzene ring and CS3, toluene. And three reactions I am considering here. This is with Cl2 HNu. This is with NBS. And this is with Cl2 500 degrees Celsius.
Sir, but BHC has no double bond.
What?
Sir, but actually benzene hexachloride has no double bond. It's just cyclohexane and chlorine atoms, six chlorine atoms.
One second, just a second. Let me. Your voice is not coming properly. 1 second. Come again, tell me.
Sir, but the actual structure of benzene hexachloride has no double bond. It's hexachlorous cyclohexane.
That is cyclohexane is this, no? Chlorine, 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 chlorine. This is
Yes, sir.
cyclohexane.
But it doesn't have any double bond.
Yeah, so I haven't written cyclohexa like chlorocyclohexane. I did not write it. I write it benzene hexachloride because the ring is benzene ring and 6 chlorine atom attached to it.
No, sir, that's what the ring is actually not benzene ring. It's just cyclohexane.
Cyclohexane is this, no, without any double bond. Cyclohexane is this, no? This is cyclohexane, correct?
Yes, sir. But
see, this ring is what? Suppose you remove this chlorine. What is this ring?
benzene.
Benzene, and chlorine is substituted on benzene. That's why it is benzene hexachloride. And why not? I numbered this chlorine atom because all these carbon atoms can have only one chlorine. When I write hexachloride with benzene, it means all the carbon atoms contains one chlorine with H. If you write benzene chlorine here, this becomes 1, 2, 3, 4, 5, 6 hexachlorocyclohexane. This one.
So he's saying that the reaction of benzene with chlorine in the presence of light will give hexachlorocyclohexane.
Oh, he's saying this double bond won't break. We'll get
Yes.
break, right?
Yes, sir.
We'll get break.
Yes, sir. Like there should be no double bond actually.
Just a second, let me cross check this. You do this question, I'll just cross check this. Benzene hexachloride forms. Okay, so just we'll check the structure of benzene hexachloride. Mm. Yeah, that's correct. The double bond should not be there. Yeah, right. So this double bond should not be there. Linden is this only. Correct this, guys. Okay. No double bond should be there. Okay, what is the product we get in this reaction, the second one? Did you finish this?
Yes, sir.
What is the product? Tell me.
Sir, it forms CH to become the first one. It will be same thing with CH to Cl.
Yes. My question, why I have given this question, actually these two questions I have given here, just to understand one simple point here. You must have done this reaction. The product would be in the first and the third one. The product, you must have written this CH2Cl here, and here also you have written the same thing. Yes or no? And here this is allylic substitution of benzene, sorry, bromine, and this would be CH2Br. This is what you did, all of you?
Sir.
Okay, now the question is why this reaction is not taking place at this carbon, means the carbon of the ring. Yes. Anyone, could you answer this? Why the reaction is not taking place on the carbon of the ring? Because if you see the previous reaction, right, the reaction takes place on the carbon of the ring and the aromaticity is lost here. Here also, however, the aromaticity maintains in the last, but for some time, like when the intermediate forms, the aromaticity is lost and then again H plus comes out to gain the aromaticity again. So for some period of time, the aromaticity has been lost here also, and here it is lost completely in this reaction, correct? Why it happens? Because now you can also think of that this was aromatic, this becomes non-aromatic. So why it is happening? Why an aromatic compound, which is the more stable compound, is converting into a lesser stable compound, right? Why this is happening here? Because the reaction is given, right? So we need to consider the reaction and we do not have any other choice. The reaction has to take place at this ring only and we'll get this product. It's not like whether this reaction is actually happening or not, right? Or we can make this reaction possible. We can give the condition which is required for this reaction and hence the reaction possible because we do not have any other choice. But here we have choice, like we have a side chain present in the ring. So the reaction takes place with maintaining the aromaticity of the ring. That's why we are not considering the chlorination at this carbon atom of the ring. So whenever we have options, we have choice, we'll maintain the aromaticity of the ring and we'll write the reaction accordingly. You got my point?
Sir, that compound is not called gamethine or linden anymore, sir.
Which one?
Sir, the new compound which you wrote, cyclohexane, hexachlorocyclohexane.
This one. No, it's linden only. By mistake, I have written my notes only by mistake. This is linden actually. This is linden. Yeah, the name is correct. The structure is this. No double bond should be there. Yeah. Okay. Right. So point with this reaction you can understand, right? Whenever side chain is present on the benzene ring, right? We always consider the reaction at the side chain, not at the benzene ring. Okay. on the benzene ring, the reaction rate is very slow. But since we do not have any choice here in the first one, we have to consider this reaction. Here we have choice. So at this place, the rate is extremely fast in comparison to the rate at this particular point. This carbon, this carbon, this carbon. That's why we are considering this reaction. So write down this note here. In case of side chain present on the ring, in case of side chain present on the ring, the reaction takes place at the side chain. At the side chain, the reaction takes place at the side chain. One second, Ayush, I'll get back. One second. Let me finish this point. Reaction takes place at the side chain in order to maintain the aromaticity of the ring. In order to maintain the aromaticity of the ring. Okay. Yes, the structure that I've written here, you can also write it as 1, 2, 3, 4, 5, 6 chlorocyclohexane, which is nothing but gamexene, which is nothing but linden, which is nothing but benzene hexachloride. All these are same thing. Yes. It's BHC only. We call it as BHC in short. Same thing. Benzene hexachloride. Okay, this is one reaction. Okay, another reaction you see which we haven't done in phenol, right? But if phenol is also there, we get the similar kind of reaction, but at ortho or para position. The next reaction you write down, we call it as chloromethylation. Chloromethylation. The reaction is benzene ring HC double bond OH with formaldehyde, then with HCl and with ZnCl2. These are the reagents we are using, and it converts into benzene ring with CH2Cl on it. Okay, this is the reaction. What happens with ZnCl2 and HCl? It gives us H plus and ZnCl3 minus Lewis acid. This H plus reacts with formaldehyde, right? Now, when this reacts with formaldehyde, H plus here, this protonates the oxygen, this oxygen lone pair, it attacks onto this hydrogen, and this converts into CH2OH positive charge on it. Okay. Now this will react with this benzene ring. Electrophile is this for this reaction. Did you understand this? This lone pair takes this H plus and pi electron shift over here. Positive charge will get. Okay. So now when benzene ring reacts with this electrophile, similar reaction, exactly similar reaction. I'm not going to write down the steps here. So this will get attached with the ring, and the product is CH2OH. This is the reaction. Okay. So we get CH2OH. The reaction medium is acidic. So in acidic medium, acid catalyzed dehydration of this, H2O goes out, and we get a carbocation which is CH2 plus and H2O. Now on this, from ZnCl3 minus, Cl minus get attached to this carbocation, and the product is CH2Cl, that is chloromethylation of benzene. Sulfonation is again exactly the same reaction we have. SO3H will get attached to the benzene ring like we did in phenol. Similar reaction we have here. Only OH is not present on the ring. Okay, I'll write down this reaction.
So one sec.
That's what Anirudh. Here the Cl minus that we are getting, it is coming from ZnCl3 minus only. So you can write down here ZnCl3 minus if you want, and this gives this Cl minus, and this attacks onto this, and ZnCl2 goes out as a neutral molecule. Okay, this reaction you see, that is sulfonation. We'll take one example, Aditya. Okay, just give me 2 minutes. Okay, so we have next reaction, that is sulfonation. Write down. Sulfonation. What happens in this? Benzene ring, and it is allowed to react with concentrated H2SO4, right? With free sulfur trioxide, SO3 also we can write, or you can simply write H2S2O7, that is oleum, and the product that we get here is SO3H. Okay, SO3H. Now, one very important property of this is sulfonated benzene, right? Sulfonic acid, it is benzene sulfonic acid. Now, when this benzene sulfonic acid, when you heat with H2O, we'll write like this: boiling with H2O or boiled H2O, like this we write. This further converts into benzene ring. So this reaction is desulfonation reaction. Desulfonation reaction. This is sulfonation, this is desulfonation. Okay, plus H2SO4 will get that. Okay. Now, what is the use of this reaction we have? I just want to tell you that. Remember the electrophile here. I am not writing down the reaction here, the entire reaction. Electrophile I have already given you. It is sulfur trioxide. It is not SO3H. This particular question they have asked in JEE exam. So you must remember this. Electrophile is sulfur trioxide. Now, what is the use of this desulfonation reaction? You see, Suppose we have this molecule. I think either your doubt is this only. Suppose I am taking a molecule which is this. Okay. Now this we want to convert this. We want to convert this into this molecule. Okay. Some of you will say that we'll do the nitration of it. HNO3 plus H2SO4. And it converts into, and it converts into this. But the major product is para, not ortho. Because we have here hindrance, we'll get this. So because of hindrance at this position, we are not getting ortho, but we are getting para. Now we'll take the help of sulfonation, desulfonation reaction. So what we do here, you see, we first allow this molecule to go under sulfonation reaction. Okay, so concentrated H2SO4. Sulfonation reaction gives you again para substituted product SO3H. Reason is same, because at ortho we have hindrance. And then this will go under nitration, HNO3 with H2SO4 concentrated. So we have only one choice left now, because the para position is occupied. So we have only one choice left. That is this. We don't have any other choice, right? And then we can easily go under desulfonation reaction when we boil this with water. So SO3H will get removed from the para position and we get the molecule which is this. So this is the reaction we have in this. The conversion of this into this, we can go by this reaction.
Sir, if SO3H is present at two positions, then which one will preferentially get desulfonated?
Two position means suppose here. See, when
Yes,
you boil
sir,
this with water, then the reaction takes place at all the positions, wherever we have
Okay.
SO3.
Okay.
Yeah. Two more reactions we have to discuss in this. And then we'll move on to SnAE reaction.
So, so is there possibility of the NO2 to rearrange itself to the para position?
No, no, it's not possible. Not like Claisen rearrangement is not possible in this.
Yes, sir.
Further, one thing is you can do, further you do the nitration. Okay. Then the reaction takes place at para.
But
Okay.
then we'll have at ortho and para.
But ortho we have hindrance. So para it can easily form.
No, sir, to the final product, which we got NO2 at ortho position,
Ortho.
to
Yeah.
that, if we do nitration, we'll get at para, right? Okay,
Yes,
sir.
then we'll get para. Yeah.
Okay, sir.
Sir,
Usually see what happens. I'll tell you one thing.
sir, SO3.
Tell me.
Sir, SO3H is meta directing, right?
SO3H is meta, yes, we can say.
So like, can meta be formed over here? Like,
No,
we
meta won't form here. Meta won't form because HNO3 here, see the reaction is from here we have started. No, substrate is this. Substrate is this, so reaction we are considering with this one. Maybe like, it is possible that NO2 has tendency to get attached at this position, right? Even if you think of this particular compound, correct? So with respect to this is the meta position. With respect
oh
to this.
yes,
And with respect to this
yes,
is
sir, yes,
ortho para position. So both way you'll get the same.
yes, sir.
See,
Okay,
actually
yes.
what happens, there are two things you can consider. Since in any ring, we have two ortho position, correct? We have two ortho position and one para position, correct? So whenever the reaction takes place, the frequency of collision means reactant molecules, the reagent and substrate when combines, the frequency of collision is always more at ortho positions because we have two ortho positions. Both ortho positions will have the attack of the reagent. That's why we always have more tendency to gain or to get ortho substituted product because we have more collision frequency. Two positions. It is only one. Right? That's one thing. But because of hindrance, sometimes para is the dominated product we get. And that you have to memorize. You cannot say logically. Sometimes what happens, ortho substituted product, and here it shows the hydrogen bonding. So in that case, ortho again is more stable. But chances are always to get more ortho substituted product because we have more collision frequency at ortho position. But there are again some conditions, hindrance, other stability factor, or if you have stability factor, it means hydrogen bonding. In that case, ortho product is stable. If you have static hindrance without hydrogen bonding, then para product is more dominating and major is that. But always collision frequency is more at ortho positions because we have two ortho position and one para position in the ring. Okay.
Yes, sir.
Okay. Now next, the last two reaction we have here, that is Gattermann-Koch reaction. It is a name reaction. Okay. I'll write down the spelling here. Gattermann, Gattermann, Gattermann-Koch reaction. Gattermann-Koch reaction, it is a synthesis of benzaldehyde. Okay, synthesis of benzaldehyde. One more reaction after this, which is similar to this, we call it as Gattermann aldehyde synthesis. Only one difference is there. Every other thing is same. Carbon monoxide with HCl and AlCl3 we are taking. The product is benzaldehyde. How the reaction proceeds, you see. First step, again HCl and AlCl3. AlCl3 is Lewis acid. Take Cl minus, forms H plus AlCl4 minus. This H plus combines with CO, carbon double bond O, lone pair negative, lone pair positive, and there is a coordinate bond like this. These two combines and it forms HC double bond O and positive charge. This is the electrophile for this reaction. So in the last step, benzene reacts with this electrophile and converts into CHO. Okay. Now this is the Gatterman-Koch reaction. Now in this only, suppose one group is present on the top on the benzene, and the group is OCH3. Could you tell me the nature of this group? Nature in the sense ortho para directing, meta directing. Yes. Orthopara, correct? Orthopara. Yes. Electron releasing. Electron releasing is orthopara, right? And COHCl AlCl3. COHCl AlCl3, it gives you this electrophile. So we get here the electrophile, which is H C double bond O positive charge. This electrophile will attach at either ortho or para position. So we'll get two products here. This is the case of substituted benzene like we had in phenol, OCH3 as it is, and we get here CHO, and plus the another product is OCH3 on the top and CHO.
Para will be major product, sir.
Yes.
So, but isn't there hydrogen bonding and ortho?
No, hydrogen bonding is not there. Hydrogen bonding is possible when electronegative element with hydrogen. And this side also we have some electronegative element. If you are considering this hydrogen, it is attached with carbon. If you are considering this, it is attached with carbon. So that's not possible.
Okay.
So hydrogen bonding is not possible, plus there will be some hindrance also at ortho position.
Sir?
Yeah.
Sir, electrophile attack OCH3?
No, not OCH3. You're talking OCH3, you said, no?
Yes, sir, OCH3.
No, not on OCH3. Because this lone pair, it is in resonance,
no, sir,
right?
because it has lone pair. Okay.
Yes, tell me.
No, sir, go on.
Okay. So this is in this lone pair. See, first of all, the nucleophilicity of pi bond is more than to that of lone pair, correct? So if you have a lone pair and a pi bond in a compound, then the reaction takes place at pi bond, not at lone pair. That's one thing. Second thing, here this lone pair is in resonance. It increases the electron density at ortho and para position. So that's how the product we get. Second, suppose if the reaction takes place here, then obviously this oxygen has to lose its electron, correct?
Yes, sir.
In that case, oxygen has positive charge,
Yes,
right?
sir.
Then how the positive charge of this oxygen will get stabilized? Any one bond you have to break. So you cannot break this bond. If you break the bond that you have been formed just now, then you'll get the same molecule. No reaction in that case. Oxygen, carbon bond also you cannot break. You got my point? You are talking about this. You see this. We have benzene ring. Suppose according to you, the reaction takes place at this oxygen. So something will get attached onto this oxygen, no? Yeah. This will get positive charge here. How this positive charge will get stabilized? Either you have to break this bond or this bond or this bond. Any of this bond you cannot break. If you break this bond, phenyl cation won't form, not possible. This bond again difficult to break, oxygen carbon bond difficult to break. If you break this, then you will get the original molecule only. It means there is no reaction.
Okay, yes, sir.
Yeah. This is the reaction we have. Now the last reaction in this, write down.
Excuse me, sir. Sir,
Tell
can electrophile be like a neutral electrophile? Like
possible. SO3 is a neutral electrophile only, no?
Yes, sir.
It's possible. Electron deficient it should be. Neutral or positively charged, electron deficient it should be. Okay.
Sir, can it happen with BH3?
BH3 is a is an electrophile, you can take that. We don't see, we have that reaction that is that reaction, one second, hydroboration oxidation reduction, correct? There the BH3 in that case, it is behaving as an electrophile only, which takes pi electron from the substrate.
Yes, sir.
Yes, so we can take any electron deficient molecule, whether it is charged or neutral, as an electrophile. The thing is, it should have the tendency to accept electron, which is only possible when it is electron deficient.
Yes, sir, got it.
Okay, yeah. The last reaction you write down is Gattermann aldehyde reaction. In this reaction, we have benzene ring. HCN we are taking here with AlCl3, H plus, and in the last we have acidic hydrolysis, H plus H2. The product that we get here is again benzaldehyde, CHO. Okay. So the reaction path here is, the first step, we have HCN with H plus, nitrogen gets protonate and it forms HC triple bond NH positive charge. Why? Because this lone pair, it takes this H plus, okay? And then it converts into, further, it takes this bond pair of electron and converts into HC double bond NH and positive charge on this carbon atom. So this is the electrophile we have here. Electrophile. CH double bond NH plus H plus comes out from the ring. Now this is imine. This bond CH double bond NH is imine. This goes under acidic hydrolysis in the last step. It converts into benzaldehyde and ammonia if also this one. Done? Did you understand the last step? Yes or no? Okay. See, the other way you can write down the product whenever imine undergoes acidic hydrolysis. What you do, since we have carbon nitrogen double bond, this double bond you have to break. So what you do, how to write down the product, I'm trying to make you understand. What you do, you write down H2O like this and H2O like this. So carbon nitrogen you consider, and here you consider oxygen hydrogen, right? So you have to break this double bond. So break this bond like this. And the more electronegative element, that is nitrogen here, the more electronegative element here goes with the less electronegative element here, which is hydrogen, So nitrogen attached with this hydrogen forms NH3. Carbon is less electronegative here. It goes with the more electronegative atom, that is oxygen. So from this we can write benzene ring with CH, OH, and OH. Two OH in the same carbon is not stable. Easily water molecule eliminates and it converts into this CH. Okay, this is the reaction we have. AlCl3, see, we are not using here AlCl3. Why? Because this H plus we are getting from the acid, right? So suppose if HCN you are not taking, you are taking here HCl, right? Then this AlCl3 will take in use, will have it in use. AlCl3 take this Cl minus forms AlCl4 minus. Correct. That's how it is. HCN we can take or AlCl3 we can take in presence of acid. So this reaction and the previous one, it is actually similar reaction if you compare. If you don't use this HCN, HCl with AlCl3, you'll get the same reaction. And the second step, we are using acidic hydrolysis. That is it. Okay. So these are the reactions, few reactions of aromatic chemistry we have done. Okay. Other reactions we have already done with for phenols. What all things you have to compare. Even you can easily understand the reaction of aniline, benzaldehyde, okay, benzoic acid. Just you need to know the group which is attached on the benzene ring. What is the nature of that group? Whether it is ortho-para-directing, meta-directing, or what? Okay. Plus, second thing, the reagent that we are using, you should take care of the the electrophile which is forming here, because sometimes in the exam they have been asked this question: what is the electrophile for this particular reaction? Right. So that's why the mechanism there is important. Okay. So this is done. Now we'll start with the next chapter we have, that is carbonyl compound. Okay, so we are going to start with carbonyl compound, and first we'll see the reactions involved in this chapter, which we call it as SnAE reaction. Okay, so heading, all of you write down. So many reactions we have done, few preparation methods we'll see, that is left. And this is this reaction that we are going to do today. This we haven't done. Okay, SnAE reaction, this we haven't done. Hence we finish this first. SnAE reaction. This SnAE, it stands for nucleophilic substitution addition elimination reaction. Addition elimination reaction. This is what the overall reaction is. Nucleophilic substitution addition elimination reaction. One second. So what is this part actually the most important one as far as the exam is concerned, because we are going to do all those name reactions here, right? We are going to do haloform reactions. We are going to do aldol, Cannizzaro, Claisen, haloform, Perkin, no-Venegal reaction, Reformitsky reaction. There are many name reactions we are going to do here. And these name reactions are the most important one as far as the carbonyl compound is concerned for the exam, right? Whether it is board exam or JEE exam, for both the things, these reactions are important. Okay, so what is first of all SnAE reaction? Nucleophilic substitution addition elimination reaction, right? Write down, this reaction is possible with acid and its derivative. So we are going to do aldehyde, ketone, carboxylic acid, all reactions here. Okay, acids and its derivative. This reaction is possible with acids and its derivative, and it takes place in both medium, acidic as well as basic. Okay, takes place in both medium, acidic as well as basic. First we'll see the basic medium reaction. Okay, suppose I am taking a compound RC double bond O L. This L is the leaving group here. Okay, this is the leaving group. Okay. Now see what reagent we are taking. The reagent we are taking a nucleophile here, a nucleophile in a solvent, and this solvent must be the conjugate acid of this nucleophile, HNU. Means what? Suppose I am taking OH minus nucleophile. Then the solvent is what? Solvent should be what? Should be H2O. If you are taking RO minus, the nucleophile, the solvent should be what? Should be ROH, alcohol. Conjugate acid. This must be conjugate acid base pair here. Preferably we'll take. It's not like with other things, it won't happen. But preferably we'll take like this. Okay? Nucleophile and its conjugate acid for this reaction. The product here we get is RC double bond O NU, and the leaving group goes out as L minus. This is the reaction takes place. Okay, if you try to understand the mechanism, see, when basic medium is there, right, then this nucleophile always attacks onto this carbonyl carbon. Because this is electronegative, so we have here delta positive charge, electron deficiency on this carbon atom because of high electronegative oxygen atom is attached, right? So this attacks onto this carbon and this goes up the pi electron onto the oxygen atom. So what we get here, we get RCO minus, this nucleophile and the leaving group. Next, what happens if this lone pair comes back to form a double bond, then this leaving group goes out, comes back to form a double bond, right? Then this leaving group takes the electron pair and goes out, and it forms RC double bond O, NU, and N minus. This is the mechanism we have.
So,
Yes.
so if the nucleophile is a better leaving group than the L group, then it won't it still give the reactant on
Yes. We don't consider the leaving group ability of nucleophile here. The bond is already there. And if this is trying to attack any negative charge particle you have, so this particle attack onto this carbon atom. Okay. Oh, you're talking about here, right? Or either
Yes,
this
sir.
one goes off. Yes.
Okay.
So if this happens, no. If the nucleophile is a better leaving group, which is usually not the case, if this is a better leaving group, then obviously this will go out. And then the reaction won't take place. We have to write no reaction here. Because you will get what? This comes over here. This nucleophile goes out. You'll get this molecule only, no? Right?
Yes, sir.
So in that case, there will be no reaction. Right? But whenever you have this kind of questions, then you have to consider the reaction. Means you cannot eliminate nucleophile in the second step here. That is understood here.
Okay, sir.
Okay. Write down the product in this reaction. CH3 C double bond OCl with OH minus. What is the solvent here we should take?
Water.
H2O. SnAE reaction. Tell me the product here we get. Is it propanone? How? Acetic acid. Okay. Yes. So the product here is CH3 C double bond OH and Cl minus goes out. But here again the product, the final product is not this. Obviously this will form, but again what happens? Acid we are getting, medium is basic. So this basic medium will take this H plus and it converts into carboxylate ion plus H2. Right. Okay, not a problem. You see this here. One thing we can generalize or we can conclude from this reaction. What happens? This OH minus as a nucleophile attacks onto this carbon. This goes up onto this carbon. Again, it comes back. Chlorine goes out of the leaving group. We'll get this. But since the medium is basic here, and this hydrogen is what? This hydrogen is acidic hydrogen. So what happens? This base extracts this acidic hydrogen from this and convert into its an ion. Right? That's why we always say that in this reaction, we won't get acid if the medium is basic. We won't get carboxylic acid as the final product. Carboxylic acid never forms in basic medium. If it forms, then it converts into a salt or an ion, because the medium is basic, it takes H plus ion and convert it into this. Copy this down and write down this point. We never get carboxylic acid as a final product in basic medium. Okay, another point you see, in this reaction overall what happens? This is the first step, this attacks over here and we get this. And this step is the addition of a nucleophile. Here, this step we get here, it is the addition of nucleophile. And here we have this step, we have elimination of leaving group. Elimination of Lg, leaving group. Okay, and that is why it is nucleophilic substitution, addition, elimination reaction. So this is the basic medium reaction we have. Next, you see acidic medium reaction. If the medium is acidic. Okay. So what happens in this? CH3, C double bond O, L, the leaving group. It takes H plus and its conjugate base is this, HNU as a solvent. And the product that we get here is CH3, C double bond O, NU, plus the leaving group goes out. Same product we are getting, but the mechanism is different. What is the mechanism here? If the medium is acidic, then the reaction starts at this oxygen. This oxygen gets protonates with this H plus of the acid, and it converts into CH3, C double bond OH, positive charge and the leaving group, which further converts into CH3, C single bond O, H, positive charge and leaving group. Okay. Then the solvent that we have, HNU, this solvent behaves as a nucleophile here. And this attacks onto this carbon atom and this forms CH3, COH, leaving group, and NU here. H plus goes out, I haven't written it here. Okay, again, this lone pair of oxygen, it comes back and pushes this leaving group out, converts into CH3, C double bond O, and done. So overall, what is happening, you just try to understand here. We had this molecule. How to write down the product? You see this. I'll take one example. Let's so example. Suppose I have a molecule and say this one, C double bond O, and a leaving group attached here. And this I allowed to react with H plus. What is the solvent that we take here? Could you tell me? H plus with what we can take?
OH.
Sorry?
H2.
What? Wait, Siddharth, just a second. Tell me first, Siddharth, I'll come back to your doubt. Okay, give me some time. What we should take here? Only water. Okay. You are saying water, I'll write down water here, H2. What else we can take? Anything. When you say anything, it means it includes everything, no? But yes, the thing is,
NH2.
sorry?
NH2.
NH2. Not NH2, NH3 we can take. We can take ROH. We can take PHOH. We can take CS3COOH. कुछ भी ले सकते हैं. Here we do not have any constraint. In basic medium reaction, what we had a nucleophile OH minus, and we were taking the conjugate acid of this nucleophile as the solvent. It means we have to add H plus. We don't have any other choice. H plus is the ion that we have to add to get the conjugate acid of this nucleophile. But this H plus we can get from any of this molecule, no? So anything we can take as a solvent over here. And the solvent that you take, according to that only you will get the product. If you want to prepare acid, you take H2O. Want to prepare amide, you take NH3 here. You want to prepare ester, you take alcohol here, right? You want to prepare anhydride, you take acid here. I'll give you with all these examples, I'll just make you understand what I'm talking about now. But the difference between the two reactions is when you have basic medium reaction, then whatever base you are taking, whether you are taking OH minus, RO minus, PHO minus or anything, NH2 minus, anything you are taking as a base. But the solvent should be the conjugate acid of this. And how do we get that? By adding H plus. So we have to add H plus into this. We don't have any other choice. PHOH for better result, right? We add H plus into it. Sorry, NH3. We add H plus into it, right? But here we don't have that constraint because this H plus we can get from any of this molecule. So that is the advantage of acidic medium reaction. We can get any possible product here, any possible compound you can form. Okay, we'll discuss all these examples. Now, why we are taking here the conjugate, acid of this? If you see this reaction, the nucleophile that we are using here, Siddharth, your doubt. The nucleophile that we are using here, right? Its concentration, it is getting consumed in this reaction. It is getting attacked over here, right? And H plus that comes out when this nucleophile attacks here, it goes up, and when it comes back, this L minus goes out. Right, this is a leaving group. Or if you take this example, this you'll understand it better. OH minus comes here, over here, pi bond goes up. When it comes down, you will get this Cl minus goes out, right? And this Cl minus is taken up by the solvent, which is HCl. It forms maybe here, right? So when you talk about the concentration of the reagent that we are using, okay, if you are taking here, I'll just take one example here, you see, then you will understand what is the difference between the two. Suppose I have taken here, what? I have taken here, OH minus I have taken, and solvent I should take H2O, but I'm taking ROH, for example. Okay, ROH. Now what happens here, that this ROH itself has the ability to behave as a nucleophile. Then this ion, which was the nucleophile we were assuming, This ion now it is competing with this solvent to attack onto this carbon atom, because both has tendency to attack onto this carbon atom, right? So in that case, you will get two different product, or mainly you will get OR attached onto this. So two possibility here, I'll just show you. Suppose if OH minus attack, you are getting an acid first. Let it be this product, whatever we are getting. We are getting an acid. Suppose the case, if this alcohol is behaving as a nucleophile, then what happens? You see, what we get CS3, C double bond O, and OR finally. So we are getting an ester. We wanted to get an acid or ion from this acid, but we get an ester. This product we do not want. And to eliminate this possibility, we are taking the conjugate acid of this nucleophile as the solvent. Now you consider H2O. Now what happens? This OH minus and H2O, whatever attacks, if this attacks or this attacks, eventually you will get OH only over here. That's why it is always better, always easier to take the conjugate acid as the solvent in this reaction. Did you get my point, Siddharth? All of you understood this?
Got it, sir.
But yes, if you want to get an ester, you can take alcohol there. Okay, this was the first thing. And I was talking about this, right? So like in the previous case, we do not have any constant here. We can take any solvent, right? As per our choice, depends what product we want here, right? So we'll discuss all these examples one by one. I'll show you. So in this one, I want you to write down, just a second. I want you to write down the product with H plus acidic medium and pH OH. So I was talking about how to write down the product. Okay, if you look at the pattern here, right? So Nu get attached with this carbon atom, will get C double bond O Nu. And how do we get Nu? Nu we can get when we remove H from the solvent. So what you do, you remove this H from the solvent and the product would be C double bond O, OPH. This is the product we get. In one step, you can write down like this. You can also consider the reaction like this. pH, OH. Okay, then the same thing. Less electronegative atom goes with more, less goes with more goes with less. C double bond O, OPH plus HCl. Did you understand this? Tell me guys, all of you.
Yes, sir.
Right. So if you want to get ether, you will get either alcohol or PHOH you can take. So what is the product you get? Suppose if you want to get an ether here, then what should be the solvent you should take? H plus with? Not ether, ester, I'm sorry. Ester. What is the product you should take? The solvent here?
ROH.
ROH.
ROH. You can take ROH here. For ether, for ester. Suppose if you want to get an acid, what should you take? This with
H2O.
H2O. You'll get an acid here. Right. So depending upon the product, you can have the choice of solvent here. That is the advantage of acidic medium reaction. Clear? Any doubt in this? No? Right. So the product, if you write down here, that would be C double bond O, OR, and this is C double bond O, OH. Can we get acid here or will we get ions?
Acid only, sir.
Acid.
Acid or ions, like in the previous case. basic medium reaction?
Sir, acid only.
Acid only, because the medium is acidic, right? So there is no ions or molecules which can extract the acidic hydrogen from this molecule, right? So we get here acid, not the ions of it, okay, not the salt of it. Clear? Okay. Write down the product in this reaction. Suppose I am taking CS3 C double bond O Br. One more you write down here. Okay. The reagent we are taking here is pH O minus Na plus pH OH. The second case, it is CH3O minus Na plus CH3OH. CH3COONA. What is the solvent here? CH3COOH. We have RNH2. NH3 is the solvent. RNHR. Again, NH3 is the solvent. Or we can take R3N. NH3 is the solvent. What is the product we get in all these reactions? Let me know once you are done. I'll write down the answers. One second, guys. Done, all of you? So the answer for this one is CH3 C double bond O OPH. This is CH3 C double bond O OCH3. This is CH3 C double bond O OC double bond O CH3 anhydride. This is CH3 C double bond O N H R, right? Alkyl amide. This is CH3 C double bond O N R R, and in this one we have no reaction. Why no reaction in the last? Because here we do not have hydrogen present. Correct. Suppose if this lone pair, how this reaction proceeds, you try to understand first. In this reaction, what happens? Suppose we have CH3 C double bond OBr. Yes, correct, Siddharth. If you have NH3, for example, so this NH3 attacks onto this carbon atom and Br goes out, or if I write down the product directly here, it would be CS3 C double bond O NH2. And how it happens, when this attacks onto this, nitrogen has positive charge on it, okay, which can later on stabilizes by the hydrogen which comes out leaving this electron pair behind, okay, and hence plus the other product we get, which is HBr here. Correct. Since this has no hydrogen here, so if nitrogen donates its electron pair, so further it won't get stabilized, and hence the reaction goes in backward direction. And there is no reaction, no net reactions we have. That's why there is no product in this reaction. Okay. Now, another thing is,
So,
like, yeah.
So you said NH3 is the solvent in the last three reactions.
So the same thing, no, if I have taken ammonia only, suppose, then you'll take
Yes.
NH2. If you take RNH2, you'll get NHR here.
Yes, so if ammonia is the solvent, then will that will tend to attack rather than RNH2 or RNHR.
See, this is, in this we are not taking ammonia as a solvent. Here we are not. That's why I did not try. I meant what? That if you take ammonia also, you'll get the similar kind of product here.
Oh.
But this is a compound we have, right? And why we don't require any solvent here? Because this itself is behaving, we have excess of RNH2. So it is behaving as a nucleophile itself, right? That's why we don't require any solvent. But if you take NH3 also here, only NH3, then you'll get this product like this one.
Yes, yes.
Okay. Okay. So another thing is what? See, you are getting different products. You are getting ester, you are getting anhydride, you are getting amide, substituted amide, you are getting, right? This is the reaction of acyl bromide. Basically, acyl halide it is. Now, this is the leaving group, hence it becomes acyl halide. Halogen is the leaving group, correct? We can have any leaving group also here. Like we can have any solvent in order to get the product. We can have any leaving group also. Like for example, you see this, leaving group could be We can have halogens as the leaving group, mainly chlorine and bromine, iodine also. We can also have OR group as the leaving group. We can also have OC double bond O R as the leaving group. Okay. OC double bond OPH as the leaving group. So we can have different leaving group here, right? And when we have this group as the leaving group, then the reaction would be for the different molecule. Like this is a reaction of acyl bromide. When you have OR, then it becomes a reaction of what? Ester. OCOR, it becomes a reaction of anhydride. It is again an anhydride, okay? So that's why I'm telling you that this chapter we are doing 2-3 different compounds, the reactions of 2-3 different compounds altogether. We are doing acyl halide, we are doing amides, we are doing anhydride, we are doing esters altogether, right? I'll give you some examples of these, leaving groups also. You can write down the product here. You see these reactions. The first reaction we have, suppose I'm taking an ester here now, okay? So the ester is, we have CH3, C double bond O, OR is the ester, and it reacts with 5 different reactions. I'll show you. 1, the first one is I'm taking CH3O minus Na plus with CH3OH. PHO minus Na plus PHOH. CH3COO minus Na plus, and then we have CH3COOH. OH minus with H2O, and we have NaNH2. What should we take? What is the solvent we should take here? NaNH2. Solvent is NH3 because it is a salt, Na plus and NH2 minus NH3. Write down the product in this. One more question we'll see. This is the reaction of ester. Another reaction is anhydride. Ester, anhydride, and the reaction we have here OH minus H2O, we have H plus H2O, we have CH3O minus, CH3OH, CH3, OH I'll write down here only, H plus, and OH minus PHOH. Write down the product in all these reactions. Done? Okay, done? See, if you're getting any confusion here, the simplest way is what? Whatever solvent is given, you just focus on that. Mechanism I have already discussed, right? Solvent you just focus on, remove H plus, and whatever you are left with, the conjugate base, you attach with this carbonyl carbon. Like for example, if suppose this CH3OH here, just one I am writing down here, CH3OH I'll write down this way, CH3ONH, break this bond. OCH3 will attach with carbon and this H attach with oxygen and the product you have, right? So the product here is this, is CH3, C double bond O, OCH3 plus we get alcohol ROH. Remember this O is here, this O is here, okay? This you take care of.
Excuse me, sir.
Tell me.
Sir, you said that if the nucleophile is a better leaving group than the leaving group itself, then reaction won't happen. Sir, so RO minus, unless R is CH3, it will be a worse leaving group than CH3O minus, no?
See, first of all, I am writing down the general reaction. We are considering here the reaction is taking place because R can be anything, no? It can be anything.
Yes,
but
sir.
if suppose, if this nucleophile attacks here and it will get attached OCH3 like this, and this pi bond shift over here, O minus, and when it comes back. So obviously, this lone pair that is forming a pi bond here, if pi bond is forming, then obviously one bond has to break, right? among these 3 bonds, one bond has to break to maintain the tetravalency of carbon.
Yes, sir.
So the one which is the weakest bond, or when it goes out, the ion becomes stable, which means the molecule, if it is a better leaving group, that will go out. So whether it is this one or this one, accordingly the bond breaks and it will go out. But here I am writing down the general reaction. Means we are considering the reaction is taking place, because the leaving group ability OCH3 and OR, you can only compare once you know what is this R group you have.
Sir, I understand.
Okay. So here I am considering the reaction. So CH3 C double bond O, what we get here? OPH. One second, just a second. OPH plus what we get? We get ROH again. So alcohol forms in this reaction. One more thing is what? If this R is not CH3 or PH, so one ester is converting into another ester. So this kind of reaction, we call it as trans-esterification. If one ester is converting into another ester, this reaction is trans-esterification. Not much important, but term you just keep in mind, okay? Here the product is CH3, C double bond O, OC double bond O, CH3 plus ROH, alcohol.
Excuse me, sir.
Yes.
Sir, in the second reaction, won't the O minus pH be like resonance stabilized? So how will the reaction even take place in the first place?
See, it's like when it is given, right? You have to take the reaction. It is stable, but OPH minus is there in the reaction. Suppose this and this mixture we have, right? Means what? You have in this solution, you see what all ions are present. We have PHO minus, Na plus, and H plus, right? So obviously this PHO minus, and when you put this molecule into this, here it will have delta positive charge. This O minus will get attracted towards the delta positive charge. In this kind of reaction, see, it's not like resonance we apply everywhere. We don't apply resonance for nucleophiles. For leaving group, you can apply. You can check the stability of the leaving group, which is going out, because that stability affects the leaving group ability of a compound. Correct. But when it is a nucleophilic addition reaction, then whether we take PHO minus as a nucleophile, no? Yes or no?
Yes, sir.
And according to you, we should not consider this as the nucleophile itself. So point is, everywhere we do not apply this stability criteria due to resonance and all. Right, we have nucleophile here. This will attack onto this carbon atom and the reaction proceeds like this. Okay?
Yes, sir. Understood, sir.
You can compare this, whether this one or this one is a better nucleophile. That you can compare. The one which is more stable is a weaker nucleophile. That we can say. But yes, reaction we can consider. Okay?
Yes, sir.
So here the product would be what? Tell me the product here.
CO O minus.
O minus. Acid won't form because the medium is basic here. What is the product we get here? C double bond O, NH2. Amide we get here. Plus alcohol forms here. Plus water forms here. Acid-base reaction in the last. And here also we'll get alcohol.
So there also we have acidic hydrogen, right?
Which one?
The last one.
NH2. No, we don't consider this because acid, see, all these are not strong acids. Carboxylic acids are also not strong acids. Okay. So this kind of acid-base reaction is possible with carboxylic acid only when COOH is there. CONH2, this hydrogen behaves as an acidic hydrogen, but it is not that strong, so that the basic medium NH2 minus takes this H plus from this. That is not clear concept.
Okay, sir.
Okay. So that's why we have this particular thing, that we won't get carboxylic acid as the final product in this kind of reaction where the medium is basic. Now you see, if you compare the previous one before this, the leaving group was halogens, right? Now it is OR, and now the leaving group is what? OCOCH3, right? And the compound changes. Acyl halide becomes ester now, and it becomes anhydride. So nothing you have to do, just instead of RO here, you have to consider C double bond OCH3 group, O, right? Instead of R, you have to consider COCH3 group. So what is the product we get here? The product that we get here is carboxylate ion, that is CH3, COO minus, plus from this also we get carboxylate ion. So 2 molecules of this we get CH3, COO minus, plus 2 molecules of H2 that I'm not writing it down. H plus if you have, then we get 2 molecules of acetic acid. Yes or no? If you have any doubt, you let me know. If you have CH3O minus, we'll get 1 ester we get, that is CH3, COOCH3, plus what we get next in this? The other product, CH3, C double bond O, OH first, and then H2O goes out, O minus, because the medium is basic again. Here the medium is acidic, so it is CH3, C double bond O, OH, plus CH3, C double bond O, OCH3, CH3, COO minus, plus CH3, COOPH. This is the product we get in this reaction.
So,
yeah.
So if we have unsymmetrical anhydride, then which do we consider as
I'll
leaving
take
group?
that example. I'll take that example. Wait.
Okay.
Okay. This is the product we get. Okay. Now, this one is symmetrical anhydride, correct? So whether you attack here or here, you'll get the same product because this part is same in both sides, right? When we have unsymmetrical, then what we'll do? Like for example, if you have this molecule, suppose this one, all these are concepts. Okay, it's not like we are doing questions here. I'm doing this in the form of question, but these are concepts. C double bond O and pH we have here, unsymmetrical. This reacts with CH3O minus, Na plus, and CH3OH. So obviously this CH3O minus will attack onto the carbonyl carbon, right? It will attack onto the carbonyl carbon. So on which carbon it should attack, that is the question. Okay, so you have to see, to understand this, you have to see the stability of this positive charge, delta positive charge, which is there on the carbonyl carbon. The one which is more stable, right, there the attack is not possible, right? So which carbon is more stable, the top one or the bottom one, the positive charge? The top one or the bottom one? Which one is more stable here?
The top one.
Bottom one. Why?
So top one, sir.
Top one. Why the top one?
It has more alpha hydrogen, so.
Okay, more alpha hydrogen. Is it correct?
So there will be resonance at the bottom.
The bottom one is resonance stabilized.
Yes, sir.
Right. Yes. Yes, Anjali, that is correct. The top one we have this thing, hyperconjugation. but this one is resonance with this ring. It's phenyl group, no, benzene ring.
Yes, I didn't
It
see
is
that.
right. So here we have resonance. Okay.
Yes, sir.
One second. Okay, so this base CH3O minus, this attack on the carbon or the positive charge, which is less stable, which is here. This attacks here and this goes out as a leaving group, this part. Okay, so the product of this reaction is what? The product is CH3CO, OCH3, C double bond O, OCH3, and this one is PH, C double bond O, O, H forms first, and then with base, we have CH3O minus. I'll write down here. It converts into PHC double bond O, O minus.
So can we also consider the positive charge density for the attack
Sorry?
of nuclear? So can we also consider the positive charge density for the attack of nucleophile?
Your voice is breaking, Tripan. I heard positive charge density on,
While the nucleophile attacks, sir.
correct?
So we can
More
consider
positive
the
charge density.
Yes, sir.
No, you cannot consider that because both things are contradictory. More positive charge density means less stable, right?
Yes, sir. So, yes, sir. Wherever
Right.
there's more positive charge density, there it will attack, sir.
No, here we won't consider that because if the positive charge on the carbon atom is stable, stable means it has less positive charge density, because we know more charge density means more unstable the molecule or ion is. If the charge you are trying to reduce by all the effects like minus effect that you have, then it is going towards more stability. So here we are considering the stability of this positive charge, not the positive charge density. If it is stable, it does not want to go under attack by the nucleophile. Right? So here we consider, yeah.
Sir, but in Grignard reagent or all that, in reduction also, you said we should consider the positive charge density, sir.
No, you see, the thing is, it's a different reaction. Grignard reagent, we have what kind of reaction? We have SN1 or SN2, right? It's different reaction we are considering. It is addition elimination reaction, that is nucleophilic substitution. So it's not like in one reaction we are considering something that we should consider in all other reactions. So in SnAE, that's what I said in the beginning only, in SnAE reaction, the positive charge density on the carbonyl carbon, that we do not consider, but we consider the stability of that charge on that carbon atom, because the attack takes place on that carbon atom. It is like this one is attacking here, right? If you have R minus, you're talking about RMGX, R minus, so this will definitely get attracted by the ion which has more positive charge density and less stable, right? So that is different. In SN1, SN2, we consider that because it is, formation of carbocation and then attack, if it is SN1. SN2, it is not carbocation formation, but yes, development of charge has an effect, okay? Because when charge is more will be electrostatic attraction pull. That happens in SN1, SN2, not in SnAE reaction.
Okay, sir.
Okay, so one thing, all of you, do not get confused with the other reactions that we have done, oxidation, reduction and all. You cannot generalize things in chemistry. It's very, you'll get confused in that way if you try to understand. So better you try to understand that this kind of compound goes under SnAE reaction or SN1 reaction or SN2 reaction. And accordingly, you can apply the condition. Correct. If you think like that, then you will have a doubt again that in SN1 we are considering the positive charge stability, and here we are not considering SN2. So it's a different reaction. Don't compare with that. Okay.
Okay, sir.
Fine. So we have this. We consider the positive charge, the stability of the positive charge on the carbonyl carbon. More stable positive charge, right? It has less tendency to go under attack by the nucleophile present into this. Could you write down the product in this one? It is a symmetrical one. And then based on this only, I'll give you one more question. We have a benzene ring. Double bond O, double bond O. And this is allowed to react with, for example, PHO minus and PHOH. What is the product we get here? Is it a symmetrical one? Yes, this attacks onto this. Anywhere you can consider. And the product would be a benzene ring, C double bond O, OPH. And here it is C double bond O, first OH and then O minus. This is the product we get. Okay, a few more we'll try to sum up this particular thing, and then we'll see the other reaction. If you have questions like this, tell me the product here. This is 1. This is 2. Tell me where this nucleophile attacks. First or second carbon, top or the bottom?
So will it attack the top one?
Your voice is not coming.
Sir, will it attack the top one?
The top one. Tell me why. What is the effect of NO2?
Minus M.
Plus.
Minus M. NO2 is minus M. Okay, NO2 is minus M. Yeah, that's right. Siddharth. This positive charge and this positive charge. This will destabilize this positive charge more because of the electron withdrawing effect. Right. This group on this carbon, it has meta position minus I effect. But because of this position here, with respect to this carbon, you see, it is para position, hence minus M. So this carbon atom is more unstable, the positive charge here, and it will get attacked by this. This is a leaving group. Basic medium, so we'll get an ion here. The product for this one is C double bond O, OCH3, C double bond O, O minus, and NO2 will have here. Okay, so this is the reaction you have to consider when it is unsymmetrical anhydride, if you have. Okay, fine. So we'll start another reaction in this, like in acidic medium reaction, what all things are possible. Okay, we'll do that after the break. Okay, we'll take a break now and then we'll start.
So if we have a more electronegative atom attached to N, then it will be minus R.
Where? Attached to where?
So in the NO2, instead of O2, if we have a less electronegative atom, lesser than nitrogen,
then
it will,
suppose we have you said CS3, something like this.
no, so instead of O2, if we have nitrogen, and
instead of
nitrogen, yes sir, instead of oxygen we have an atom which is less electronegative than nitrogen, then will it be plus R?
So it is NH2, for example.
Yes sir.
Then it is plus N. Yes.
Oh, okay.
Okay. Here actually what happens, you see, you probably if you get this bonding, you will understand. I got this doubt. You are thinking of that this nitrogen has lone pair. Then why not it is plus M? I think it is, right?
Yes sir.
Thing is what? Here we do not have lone pair on nitrogen atom. Actually, NO2, the structure is this. And just a second, is like this. So lone pair of nitrogen cannot have 4 bonds, no? And since I did not put any charge, it means one of the bond with oxygen is a coordinate bond. Means the lone pair which was there initially, this lone pair, it has donated to the oxygen, and hence a coordinate bond we have here. We do not have lone pair here, hence it cannot donate to the ring, and hence it is not plus M, but it is minus M. Got it?
Yes sir.
If you see NH2, there is no coordinate bond here. NH2 simple it is. Because nitrogen has 3 bonds, lone pair is present and hence it's there. So in NO2, whenever it is attached to the ring, nitrogen does not have lone pair present on it, and hence it is not plus M. Got it?
Yes sir.
Okay. Okay guys, take a break now. We'll start at 7. Okay. Thank you. Take a break. Hello guys, can we start? Hello. Okay. So, okay, so we've seen this reaction, right? We have anhydride and how this reaction takes place. Correct. Now, this particular example you see, we have dicarboxylic acid, which is this one. C double bond O, OH. And we are heating it. We are heating it. Okay. One more example. We have phthalic acid, and phthalic acid is a benzene ring, C double bond O, OH. And here also we have C double bond O, OH. And we are heating it. C double bond O, OH on the top. And on the bottom also we have C double bond O, OH with alcohol, ROH. Medium is acidic. Right, the reaction is taking place. So these two reactions, these are basically the heating effects of dicarboxylic acid that we have already done, right? And if you remember, if there are two carbon atoms in between the carboxylic acid and we heat it, then H2O molecules eliminates, right? If you have 0 on one carbon atom, CO2 eliminates, if you remember that. Then this converts into an anhydride, which is this. Double bond O plus H2. Correct. This molecule, again, you are heating this, two carbon atom we have in between the two carboxylic acid group. Let me know if you're not getting it. Benzene ring, C double bond O, C double bond O, water eliminates, so both carbon atom joins with oxygen and H2O we have. Right, like this. Water elements. Here also, water elements like this. And this carbon joins with this oxygen. Now here we have solvent, and in presence of solvent, we are heating it. So this gives you SnAE reaction when we heat this in presence of solvent. So the product here is C double bond O, OR, and this is C double bond O, OR, plus 2 molecules of H2O. So you see these two reactions and this reactions, both are different reactions. This one is the last one that I have given. This one is SnAE reaction. Why? Because the solvent is given into this one. Solvent is given. This two reaction, we are just heating it. This one and this one. We are just heating these two compounds. So here we are not using the concept of SnAE. These are the heating effects. Heating effect that we have done. Heating effects on organic compound. Okay. So when you have solvent given, then we consider SnAE reaction. If not, then heating effects we consider.
Sir, in the bottom one, OH behaves as leaving group, sir.
OH, no, it's an acid medium reaction. No, here.
Yes, sir.
No, for this reaction, the mechanism is a bit different. Okay, this goes up. See, actually what happens when this attacks onto this, right? ROH here. We can also consider one thing here, that this H plus, it protonates the oxygen here and H2O goes out, right? And then this behaves as a nucleophile, attacks onto this. That way also you can consider. I'm just giving you one reference of this reaction, that if the solvent is given, then we'll go by SnAE mechanism. If solvent is not given, then we simply heating it, so it is heating effect. And if you remember, if oxalic acid, if you heat, what is the product we get into this one? Could you tell me? You forgot. See, if this is the molecule, I'll write down here one general expression. If you can recall, HOOC, CH2N, and COOH. And if you heat this, so depending upon the value of N, will get the product. If N is 0 or 1, then CO2 eliminates. If N is 2 or 3, then H2O eliminates. If N is 4, 5, then both CO2 and H2O eliminates. We discussed this in heating effects of compounds, if you remember. So here we are using heating effects. Here, if reaction takes place, it gives you this product according to SnAE mechanism. We can have anything here. If you are getting confused with OH here, you can take RC double bond OCl, C double bond OCl. Then it is SnAE.
Sir, for that reaction, is temperature necessary or no?
Sorry, which one?
Temperature is not required, right?
No,
With the-
temperature they don't give. Simply we are heating it. Just heat is required.
No, sir, I'm telling for the last reaction, do we need to heat it or will reaction happen just like that?
No, nothing. Solvent is given. You don't have to think of temperature or heating effects here. Just you consider SnAE reaction. Let's see, in SnAE we haven't discussed about temperature thing anywhere. Okay. So this thing you must take care of when you have to use heating effects and when you have to use SnAE reaction. Okay. One similar reaction you see, which is not SnAE here, but one similar reaction you see here. Write down the heading, benzene sulfonyl chloride. Benzene sulfonyl chloride. What is benzene sulfonyl chloride? It is pH S double bond O double bond OCl. Right. And this we call it as Hinsberg reagent. Hinsberg reagent. This also gives the similar reaction like we had in acyl chloride. Simply you can consider S double bond O as carbon double bond O to understand this reaction. This similarity you can consider. Instead of sulfur, we have carbon, and we have in carbon we have sulfur, and we have similar reaction. So this benzene sulfonyl chloride, which we also call it as Hinsberg reagent, when it reacts with 1 degree amine RNH2 and then with R2NH 2 degree amine and then with R3N that is 3 degree amine, the product that we get here, this HNCl goes out and the product is, here we get PH S double bond O NH2. It is PH S double bond O N R R, and this one, since we have no hydrogen, we have no reaction here. 1 second, guys.
Sir, in the first one, it should be NHR, no, sir?
Just a second, I'll check. Let me take this screenshot. 1 second. Yes, tell me. NHR. First one we have NHR, correct. Because one H will go on. So NHR. And here we have no reaction. Well, exactly similar reaction we have. You can keep this in mind. Now, one more reaction if you see here, which is not actually related to this particular topic, but just for your, just for a revision or your understanding, I'll just discuss it here. Suppose you have an alcohol, and this alcohol, you want to convert this into RCN, alcohol to cyanide. What you will do, you will just add KCN here, right? Okay, KCN you add so that the reaction undergoes SN1 or SN2 mechanism, and this OH goes out as a leaving group, converts into this. But since OH is not a good leaving group, right? Not a good leaving group. Good leaving group. This reaction is not possible. Okay, this is actually not possible. So for this, what we do, I think I've discussed it, but quickly I'm just going through it. We convert this into a good leaving group with the help of a compound, and that we call it as, I'll write down the reaction here. Yes, correct. So the reaction is ROH, alcohol, and this is allowed to react with tosyl chloride. Why I'm discussing this here? Because again, here also you see it is a similar kind of structure. pH SOCl here, pH only one CH3 is present here. This we call it as para-toluene sulfonyl chloride. Para-toluene sulfonyl chloride. Okay, this converts into HCl, and this H and this Cl combines, forms HCl, and we get here the benzene ring, S double bond O, OR, right? And this one is a very good leaving group. This group is a very good leaving group. Very good leaving group. So when this goes under SN2, suppose reaction I am considering with KCN, then this CN minus attacks onto this alkyl group, and this goes out as a leaving group, and it converts into RCN. right? Plus the leaving group we get here, which is this negative charge on this oxygen. Okay. So from this we can convert a poor leaving group into a very good leaving group, and then the reaction proceeds like this. Okay. That is the use of benzene sulfonyl chloride, which also goes under the similar kind of reaction I have given you here. Okay. Now the another thing here is the reaction of amide. Reaction of amide, it is there in nitrogen containing compound chapter, but this also shows SnAE reaction, like this kind of reaction. We have discussed RCONH2, the reaction of RCONH2. I'll show you a few reactions here. The reaction of amide, if you see, did you copy the previous one, all of you?
Yes, sir.
Yes, sir.
Okay. Suppose we have RC double bond O NH2 reacts with R2NH, secondary amine I'm taking here, R2NH, secondary amine. This converts into RC double bond O, N, R, R, and NH3 forms ammonia. Okay, how this reaction goes, you see. In the first step, we have R2NH, correct? So R2NH, this lone pair, this attacks onto this carbon atom. This goes up and it forms RCO minus NH2. And here we have N, H, and 2 alkyl group present here, positive charge on nitrogen atom. Now to stabilize this positive charge, one of the H plus comes out, leaving this electron pair. This H plus comes out, and this protonates this particular nitrogen atom. So it's like it comes out, and this nitrogen has a lone pair, so it takes up this H plus from this. Okay, and then it converts into RCO minus 3 lone pair. We have NH3 positive charge, and we have NR2. So the next step, when this comes back, this pair of electron to forms a pi bond here, this goes out as a leaving group, and the product is RC double bond O NH3. So this is SnAE reaction.
That's NR2, right?
Sorry?
Isn't it NR2 in the last step?
NR2. Oh, my bad. NR2 plus NH3. Okay, this is how the reaction proceeds. This is SnAE reaction. Okay, we have few reactions, that is dehydration reaction of amide. Those are not SnAE reaction. I'll just write down here. Mechanism we won't see. We'll see that later in amines chapter. Right. So there are few reactions which are not SnAE. You must keep that in mind. For example, if I write down the reaction of RC double bond O NH2 amide with 3 reactions we have here. The first reaction is the reaction with P2O5. These are dehydrating agent. Okay, you have to memorize this reaction. PCl3. Few reactions we have seen already in reaction mechanism. PCl3. NaOH. We are heating this with NaOH. In all these reactions, the product we get is RCN, cyanide. RCN cyanide, RCN cyanide, and water molecules eliminates. These reactions are not SnAE reactions, but these are dehydration dehydration of amide. These are dehydrating agent. Okay, this is one thing you must remember. This is not SnAE reaction, but these are dehydration reaction in which the removal of water takes place and forms cyanide. Okay, so amide few reactions we must remember. Okay, now the most important reaction we have next. You copy this down. I'll go to the next page. Done. The most important reaction, that is aldol condensation. Have you heard this name? Aldol condensation reaction. What is aldol condensation? What happens in this reaction? You have done this in school? Okay, you haven't done it. Let it be. Okay, I'll show you what. Write down first of all. This is the reaction of aldehyde or ketone. Both we can consider. The reaction condition is presence of alpha hydrogen in dilute basic medium. In dilute basic medium. Okay, so we can take base for this purpose, and mostly we use dilute NaOH for this. Dilute NaOH. We can also take dilute BaOH whole twice, but mostly you will get NaOH only, or OH minus simply it will be written. Dilute K2CO3 also we can take for this purpose. Okay, these are the reagents. So presence of alpha hydrogen is the condition, right? If alpha hydrogen is not there, then aldol condensation reaction is not possible. Right? For example, you see, if we have CH3, C double bond OH, this molecule, CH3, C double bond O, CH3, this molecule, H, C double bond O, H, benzaldehyde, C double bond O, H, cyclohexanone, double bond O here. How many of these molecules aldol condensation reaction possible? This kind of question also you will get. Okay, not in JE, but yes, in other exam, they'll give you a few options, 4 options, and they'll ask you in which of these molecules aldol condensation reaction possible. Like in this one, you see. Tell me the number of molecules which gives aldol condensation reaction. What is the reaction we do not know now, but yes, condition you know, you can easily say. Tell me the number. 7, okay, 3, okay, 4, 5, 6, 6, 6, okay. So first of all, we have alpha hydrogen in this is possible. We have 3 alpha hydrogen. At least 1 requires. We have 3, fine. We have alpha hydrogen, possible. No alpha hydrogen, no alpha hydrogen, not possible. Yes, we have. Yes, we have. No alpha hydrogen. Yes, we have. No alpha hydrogen. So 1, 2, 3, 4, 5.
The last one is there. No, sir.
CH3.
1, 2, 3. In this we do not have. In this we have. In this we have. In this we do not have. In this we have. That's the last one we have. This side. This side we do not have. This side. Yeah. So this is also possible because this side we have alpha hydrogen. Correct. So there are 6. No, 1, 2, 3, 4, 5, 6. Yeah, 6 molecules which has alpha hydrogen, and hence it shows aldol condensation reaction. Now, what is aldol condensation reaction? First of all, we see. Suppose we have a molecule that is acetaldehyde, and we always take 2 molecules of it for this reaction. Right? If it in the reaction also, if it is given only 1, you have to consider 2. Right? Acetaldehyde goes under the reaction OH minus dilute. Dilute base we require OH minus. So it converts into CS3C OH CH2 C double bond O H. Converts into this. Okay. This, the name of this compound is, if you see, this is alpha carbon with respect to this, and this is beta carbon. And in general, we call it as beta hydroxy beta hydroxy aldehyde. Beta hydroxy aldehyde. And since we have condensation reaction, so it goes under condensation when we heat this. When we heat this, and we get condensed product here. Condensed product. Water molecule eliminates into this one. Okay. So first of all, how this reaction takes place and what is this aldol, first of all, right? So aldol is, it's a general name, and aldol is beta hydroxy aldehyde or ketone, both you can consider. Beta hydroxy ketone is aldol, beta hydroxy aldehyde is aldol. Like for this one, it is beta hydroxy aldehyde, it is aldol. And then you heat it, condensation takes place, the entire reaction is aldol condensation. Right, so from here to here, it is aldol condensation. From here to here, it is only aldol reaction. right? If you do not give, I'll discuss that later in the last. Okay, the whole reaction, the entire reaction is this. How this reaction takes place, I'll just explain this here. See, first of all, the medium is basic. So we have first step, we have OH minus basic medium and CS3OH. So CS3COH is this. And here we have the hydrogen. Okay, so this base takes H plus from the alpha carbon. That is the alpha hydrogen. And that's why the alpha hydrogen is required for this reaction. It extracts S plus and it forms what? H2O plus we get here the conjugate base of this compound, which is this C double bond OH. Okay, and the reaction is reversible in nature. Okay, this one we can draw the resonating structure for this. This comes over here and this goes up. And it forms CH2 double bond, C single bond O minus and H. This we call it as enolate ion. Enolate ion, the intermediate for this reaction. Intermediate for this reaction. Now this one, this intermediate ion that you have, it forms, this forms, why it forms? Because it is resonance stabilized. So this one is enolate ion, this one is enolate ion, right? Resonance is stabilized, but this is the base we have here. Now this is the base which attacks onto the carbonyl carbon in the next step. I'll show you how. In the next step, what happens? This one and the molecule, because we take two molecules of this. So one molecule we have used here, the other one is this, which is CS3C double bond O H, and we have CH2 single bond C double bond OH. So we are using this one only here. It forms because it is stable through resonance. Okay, so this attacks on the carbonyl carbon. Right here it attacks, and this pi electron moves up onto this oxygen. This step is the slow step, RDS of the reaction. Okay, the entire thing is very important. That's why I'm going very slow over here. This is the most important reaction you can say. Okay, aldol and Cannizzaro for this chapter. So it converts into, you see, this CS3 I'll write down as it is. This carbon which is being attacked by this O minus we have here. This hydrogen will have here. And then the another molecule which is CH2, C double bond O and H. Okay, this is what we get. RDS of the reaction is this. Now, in the next step, this gets protonates because the first step you see it forms water, and the O minus here, it protonates from the water molecule. Right, it takes this H from this particular molecule and it converts into CH3, CH, OH, CH2, C double bond O, H, and plus OH minus. So the concentration of the base is maintained. Okay, The first step it consumes, and the last step it eliminates, and the concentration of the base is maintained. This one you see, it is beta hydroxy aldehyde. Okay, so this one, like I said, beta hydroxy aldehyde or ketone, we call it as aldol. So this one is aldol. It is not aldol condensation till now. Okay, when it becomes condensation, that in the next step, if you heat this, okay, so if you heat this, then what happens? You see, the molecule is CH3CH OH CH2. I'll write down H like this, C double bond O and H. So when you heat this, then water eliminates and it forms CH3 CH double bond CH single bond C double bond O H plus. This is what the product we get. We will also get one minor product. This one is the more stable one. One is the double bond. The alkene is more conjugated here, more substituted. Second one, it is pi sigma pi resonance stabilized. Okay, conjugation we have here. This is the stable product we have. Unstable product is what? When this H and this OH comes out, we'll get a double bond here. That is the minor product. Okay, so this one we get alpha. You see this? It is alpha position, it is beta position. So we get alpha beta unsaturated aldehyde. Right? Alpha beta unsaturated aldehyde. So the product of aldol condensation is, it is alpha beta, it gives alpha beta unsaturated aldehyde or ketone. Copy this down. Dehydration and condensation actually see, dehydration is mainly it takes place in presence of a reagent. Condensation is generally, you can say it is heating effects kind of. You heat it and the molecule condensed, eliminate some smaller molecules like water, NH3. And dehydration, second thing is what? The dehydration is more specifically, it is used for alcohol when water molecule eliminates. That is dehydration.
Okay.
But condensation includes water as well as smaller molecules like ammonia, HCl, etc.
Yes, sir.
But as far as the mechanism is concerned, condensation is more about heating the compounds. Dehydration in presence of a catalyst generally happens.
Yes, sir.
Done? So what happens overall, you see, did you copy this, all of you?
Yes, sir.
Okay. So overall, what is happening in this reaction, you see? We are having, the reaction is, we are having two molecules of CH3, C double bond OH, dilute base, we are heating it. So it converts into CH3, CHOH, CH2, C double bond OH, which is aldol. And if you heat this, then this converts into CH3CH double bond CH, single bond C double bond OH plus H2, right? So if in the reaction, you must remember, I have written this in 2-step. Sometimes what happens, they don't write here this particular sign. If they don't write this, that we are heating it, you won't get the condensed product. Condensation is not taking place there. OH and dilute OH, if you only have, then this is the answer for the reaction. If you are heating it, then further aldol goes under condensation reaction and gives you alpha beta unsaturated aldehyde or ketone. Clear? Okay. Could you write down the product in this reaction? Take two molecules of it. Write down the product. Try this. Okay. So what is the product we get? The aldol for this molecule is, see what happens. How do we write down the product? See, one molecule we have CH3, CHO, and it is CH2C double bond OH. So what you do, from the alpha position, you remove one hydrogen simply. One molecule you write like this. Alpha position, whatever hydrogen you have, you remove hydrogen, at one hydrogen from this. Right. So to make you understand, I'm just writing down this. You remove hydrogen from the alpha position. Okay. So I've removed one. And then this attached with the carbonyl carbon of the other molecule, which is this one. Suppose it's the carbonyl carbon of the next molecule. And the carbonyl carbon contains one OH. So this is the aldol we have. Did you get it? Tell me, is it clear? So with dilute OH minus, you'll get this. Suppose if I have given here heat, then further this goes under condensation reaction minus of H2O. So we always write alpha beta unsaturated. Right? So alpha beta position, this H and OH goes out, and the product of the molecule is this one. Any doubt in this? Any doubt in this? Tell me. If you try to understand the mechanism here, what we'll do from the base, it takes the alpha hydrogen. So it forms double bond O and one negative charge here. Now this attacks as the nucleophile on the other molecule. It goes up. So we have this double bond O and we have O minus here. Then with H2O, the protonation takes place of this O minus. So it converts into this OH and double bond O. And then we heat this, H2O eliminates, you get this product.
So,
Tell me.
so if we had a double bond O on the exact opposite carbon atom,
Sorry, what?
if we had another oxygen atom at the exact opposite carbon atom,
Here.
yes, sir, then would we get like two bridges?
If you have here again, then at both the position the reaction takes place. No.
Yes, sir, so we
No.
get like
At a time reaction takes place either at this position or this position. Any one you can consider for the reaction. Right.
yes, sir, but finally we get like two bridges sort of, right?
No, it's not like that. It's not like that. Means depends. If excess of base you are taking, if options are like that, then you can consider. But since we are not considering excess of this here, only one point we are considering the reaction. But if you are considering one more thing over here, one more double bond O, then reaction takes place for the first thing, reaction takes place either here or this position, means you'll get first this. And then again, if excess of base is there, then the reaction takes place at this position, and then maybe you can get the other product. But I haven't seen those kind of compounds in aldol condensation reaction. If you have the question that you are asking, if you have double bond O here, and you have options like this, then you can consider that particular product if the base is mentioned here is excess. Understood?
Yes, sir.
Okay. So once you practice like this, you will understand that what product will get over here. You don't have to draw the mechanism. If you do this, it'll take a lot of time in the exam. So I would request, I'll share the sheet also later on, not today. You will understand that when you practice, you will get it, how to write down the product directly. Okay, one more question you see. If you have this molecule, CH3C double bond O, and here we have benzene ring, dilute OH minus, and we are heating it. Write down the product. Are you done? See, obviously the base will take H plus from this carbon because here we do not have any alpha hydrogen, right? And then this C minus attacks onto the carbonyl carbon of the other molecule. So that would be, we have CH3, the aldol that we get here, COH, PH, CH2, C double bond O, PH. Is it clear? Is this the molecule you get?
Yes, sir.
Tell me.
Yes, sir.
See again, see Aditya here, what happens? Again, when you draw the mechanism, you'll understand. Just one step I'll draw here, you'll get it. What happens, this OH minus takes this hydrogen and we get here CH2 negative C double bond OPH. Okay. And then this attacks on the another molecule, which is C double bond O pH. This attracts over here, this goes up, and it takes H plus from water. So what we get here, you see, we get CS3 this side, CO minus, which protonates from water, OH, pH, then CH2, C double bond O, pH. This is what we get. Clear, Aditya?
Yes, sir. Yes, sir. I got it, sir. Thank you, sir.
Okay. And then since we are heating it, so when you heat this, this H2O goes out and it converts into C double bond CH, C double bond O pH, and pH.
Sir,
Yes.
sir, we can see the stability of phenolate ion to compare the rate of reaction.
Stability of intermediate ion.
Yes, sir.
Okay. You check the mechanism. What is the RDS?
Sir, it's the next step, but how do we compare the stability of the next intermediate?
Stability of the intermediate ion you're talking about.
So,
You will
no, so
have
the
that.
RDS, the
Huh.
RDS is the next step you told.
Yes,
After it
next
adds
step.
to the. So
Yeah,
how do
so
we
we'll
compare the stability of that?
see. I'll just show you that reaction. I'll go back just a second. RDS is the attack of enolate ion, correct?
Yes, sir.
Mechanism is here, I guess. Here you see this one. Yes, this one is the RDS, correct? Means the rate of this reaction depends upon, first of all, the positive charge density onto this carbon. If it is stable here, then this attack is difficult. So you can compare the stability of this positive charge, or you can also compare the stability of this enolate ion. Okay. So here in this case, the simplest one, we won't compare this. Now, suppose if you have, see, if they ask you to compare the rate of the reaction, they'll give you different molecules, correct?
Yes, sir.
Suppose you will have one molecule which is like this, CH2, chlorine, C double bond O, H, correct? So you'll get the enolate ion here. Yes. So this two, if you compare, just a second, you'll get here, this H won't be there. So this two, if you compare, which one is more stable?
The chlorine one.
Chlorine one is more stable. So this attack will be less, right? Hence the rate of the reaction in this case will be less in comparison to this. So when you have rate of reaction, then they'll give you different molecules and they'll ask you to compare the rate of the reaction. There you can apply the concept of GOC.
Okay, sir.
Okay.
Yes, sir. Understood.
So write down in this, the RDS, the rate of reaction, is the attack of enolate ion. Is the attack of enolate ion. Okay. So I'll just remove this, not required here. One more question you see. Till now we have discussed, okay. Okay, fine. We'll discuss it then because it will take some time. See, one thing is I tell you here. You have to take two molecules. Like you see here, I haven't mentioned two, but we are considering two here, right? You can also take two different molecules here for aldol condensation. For example, you see this HCHO. Does it go under aldol condensation possible with this?
No, sir.
No, right? It's not possible. But it does not mean that it won't take part in aldol condensation reaction. What do you mean by this? Correct? What I said, aldol condensation is not possible with this. But it does not mean that it won't take part in the aldol condensation reaction. How it is possible? It is possible when you take one molecule of this and another molecule of this? Then it is possible, right? Yes or no? Tell me. Dilute OH minus and we are heating it. What is the need of alpha hydrogen? Anybody?
So it acts as an acidic hydrogen.
What is the need of alpha hydrogen? To take H plus ion, like, so that the base will take H plus ion, correct? So this OH minus has to take one H plus from the alpha position. So here it won't have, we won't have here. So obviously this won't give H plus ion to this base, but this base will take H plus ion from this molecule. So when you are taking two different molecules, then formaldehyde can be a part of aldol condensation reaction. Are you getting my point?
Yes, sir, understood.
Understood? Just a second. One second. Okay. So in this one, the product would be, we don't have any choice, but we have to, the OH minus will take H plus from this molecule, and this converts into the enolate ion, which is this C double bond OH, and then this will attack on to the carbonyl carbon of the other molecule, which is this, it attacks over here, and it converts into, this goes up, it converts into H. Can I write down this directly? OH on the top, H here, CH2, C double bond O, H, and then it converts into, on heating, H2O goes out and it would be CH2 double bond, CH single bond, CHO. Did you get this reaction? Understood this?
Yes, sir.
One last thing here.
Yes, sir.
One last thing here. Rate depends upon the concentration of enolate ion, the stability of enolate ion plus the stability of positive charge on the carbonyl group of the other molecule. Okay, I'll continue with this reaction. Okay, there are a few things we have to discuss onto this. Let me finish this first. Okay, I'll continue in the next session with this reaction. Now, this reaction where you are taking two different molecules of aldehyde or ketone, right? Two different molecules of aldehyde or ketone. Even you can take one aldehyde and one ketone also. When you are taking two different molecules, this kind of reaction, we use a separate term for this. And this kind of reaction, we call it as cross-aldol condensation reaction. This one is cross-aldol condensation. When you're taking two different molecules. Okay, so always keep this in mind. Formaldehyde does not show aldol condensation reaction. It doesn't mean that it won't take part in aldol condensation reaction. Okay, even all those molecules where there is no alpha hydrogen present can be a part of aldol condensation reaction. Understood?
Yes.
Okay, so there are a few more things we have to discuss here. Okay, we'll continue with this reaction only in the next class. Okay, and please let me know because there are many things going on parallelly in other batches. So I got confused that where is going what. Correct? So we'll continue with this aldol condensate. It is not finished. Okay, remind me in the next class. Okay, guys. Thank you. Take care. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.